A ski jumper leaves the ramp at an angle of 11 degrees above the horizontal, 3 meters above the ground. The ground slopes downwards at 33 degrees from this point. So we have the ski jumper leaving here, and that's 3 meters above the ground. So this distance here is 3 meters. Then the ground slopes at an angle of 33 degrees. So this angle here is 33 degrees. The jumper lands 140 meters down the slope. So this distance is 140 meters, and the ski jumper is going to follow a trajectory that looks something like that. Okay, and you have to fill out the table completely. This is similar to an earlier problem in which you have a ball rolled off of a high table at 15 meters per second. The floor beyond the table slopes downward at a constant 5 degrees below the horizontal. So if this was the problem with the table, it's a 0.8 meter high table, so this distance would be the 0.8, and this would be the floor sloping down. In this case, this angle would be 5 degrees. Okay, so you can use that to help you when you solve the problem with the ball and the table. Okay, so I have to finish drawing the vector diagram here. So the skier leaves the ramp at an angle of 11 degrees above the horizontal. So that is the angle for the initial velocity. So that's like this. This is 11 degrees. And then when I draw this vector, I want to end right above where the skier hits the ground. So this is v1 times delta t, and this vector going straight downward, that's 1/2 the acceleration times delta t squared. This is the path that the skier follows, and this is the direction of the initial velocity. Because the skier is accelerating downwards, the path that the skier follows is always beneath the initial velocity vector after the first point. Okay, now I can use this to fill out my table. Let's say the origin is where the skier starts. So r1x is equal to 0, r1y is equal to 0, t2 is equal to 0. And acceleration in the x direction, if I look at the ski jumper here, I have force of gravity acting downwards, which means acceleration is equal to negative 9.8 if upwards is positive. In the x direction, the acceleration is equal to 0. And, okay, so that's everything that we can put in for now. And then, do I know? I do not know what the initial velocity is. I just know the angle is 11 degrees. Okay, so I almost have my vector diagram here. The last thing that I would need to do, I'm going to do it in a different color because it's kind of crowded already. This vector here is delta r. Now actually, rather than using that vector delta r, let me redraw it here. That vector delta r has an x component and a y component. So this is delta rx, and this is delta ry. This angle of 33 degrees I can use to break down the 140 meters into an x component and a y component. So the 140 meters is not the same as delta r. So delta r goes from here to here, and the 140 goes from the base of the cliff to where the skier lands. But if I break the 140 meters down into components, so that would be from here to here, this would be 140, this is 33 degrees, so this would be sine of 33 degrees, and this would be 140 times cosine of 33 degrees. So delta Rx is equal to 140 times cosine of 33 degrees, which is 117 meters. Okay, so this is 117 meters. And the delta Ry would just be, so delta Ry goes from here to here. That is from here to here. So that's the 3 meters plus 140 times sine of 33 degrees, This is 76.2 meters. So the magnitude of delta Ry is 3 meters plus 76.2 meters. That is 79.2 meters. But it's pointing downward, so we said upward was positive. So this would be negative 79.2 meters. Okay, now what else can I figure out from my diagram? So I looked at the delta r vector. Now I want to look at the initial velocity. If I do the x component of the initial velocity that's going from here to here, that must be equal to delta rx. So I have v1 times delta t, the x component, that would be cosine of 11 degrees, is equal to delta rx, which is 117 meters. Okay, so the x component of this vector has to equal the x component of the delta r vector. Okay, now I think I'm still stuck because I don't know the initial velocity and I don't know delta t. So now I'll look in the y direction. In the y direction, v1 delta t, if you look at the y component, this would be v1 delta t times sine of 11 degrees compared to this vector here. So if I take the magnitude of this y component of the initial velocity times delta t and add to it this distance from here to here, which is 76.2, that gives me the entire distance, which is 1/2 the acceleration times delta t squared. Okay, so looking in the y direction, I have 1/2. Now it's the length of this vector, so it would be positive 9.8 meters per second squared times delta t squared is equal to v1 times delta t times sine of 11 degrees. That's from here to here. So this is v1 times delta t times sine of 11 degrees, plus, to make up this entire distance, I have to add to that 79.2 to go all the way from here to here. So this is plus 79.2 meters. Okay, so this distance here, that's the v1 delta t sine of 11 degrees plus the 79.2 meters, which goes from here to here, makes up the entire 1/2 times g times delta t squared. All of those are lengths, and so everything here is positive. If you compare that to what we would have if you use the kinematic equations, v2x is equal to 117, delta rx is equal to 117, and that's v1x times delta t. v1x is v1 times cosine of 11 times delta t, and ax is 0. So this is our position kinematic equation in the x direction. And the next one would be our position kinematic equation in the y direction, just rearranged a little bit. If I bring this over to the other side, then I have negative 9.8. That's what I have here. Then I have v1 times sine of 11 is v1y. So that's what I have here. And if I bring this over here, it'd be negative 79.2. That would be delta ry, which is negative. That's why the negative sign is in our table here. Okay, so these would come from our position kinematic equations. And at this point, I have 2 equations and 2 unknowns. And so I can solve for those unknowns. Let's solve this for delta t. So I have delta t is equal to 117 meters divided by v1 times cosine of 11 degrees Actually, instead of doing that, let's bring the v1 back over to this side. So I have v1 delta t is equal to 117 meters divided by cosine of 11 degrees. Then I can take this v1 times delta t and put it into my equation here for v1 times delta t. And since that's the only place that v1 appears in this equation, now I'll just have one unknown when I rewrite this. So 9.8 divided by 2, that's 4.9 meters per second squared, times delta t squared is equal to 117 meters. Then I have sine of 11 degrees divided by cosine of 11 degrees. So let's just call that tangent of 11 degrees plus 79.2 meters. Oh, and this is beautiful because I'm not even going to have to use the quadratic equation here. I can just solve for delta t by dividing both sides by 4.9 and taking the square root. So I have delta t is equal to the square root of 117 meters times tangent of 11 degrees plus 79.2 meters divided by 4.9 meters per second squared. Take the square root and you get for delta t 4.56 seconds. We can take that and put it in our table. And then we still have to find the initial velocity and the final velocity. Well, I can find the initial velocity now if I go back to this equation here and now divide by delta t. I have v1 is equal to 117 meters divided by delta t times cosine of 11 degrees, and that gives me 26.14 meters per second. And then v1x is equal to v1 times cosine of 11 degrees. v1y is equal to v1 times sine of 11 degrees. So the vector v1 points in the same direction as this vector, but the length is different because you're not multiplying it by delta t. So I have this vector v1, this angle is 11 degrees, and this is v1x, and this is v1y. So v1y is, there you go. Okay, so this is v1, this is 11 degrees, this is the x component, this is the y component. So v1 times cosine of 11 degrees, that's 26.14 times cosine of 11 degrees, and that gives me 25.7 meters per second. And v1 times sine of 11 degrees is 4.99 meters per second. Those are both positive, positive x direction, positive y direction. Take that, put it in my table up here. So I have 25.7 meters per second and 4.99 meters per second. Because the acceleration in the x direction is 0, v2x is equal to v1x. So v2x is equal to 25.7 meters per second. And then the very last step is always to use this equation here, the velocity kinematic equation in the y direction, to find v2y. And we're not going to draw a vector diagram for that. We're just going to use this equation here. And so finally, I have v2y is equal to v1y plus acceleration times delta t, acceleration in the y direction times delta t. So v2y is equal to v1y, that's 4.99 meters per second, minus 9.8 meters per second squared for the acceleration times delta t, which is 4.56 seconds. And that gives me negative 39.7 meters per second. It should be negative because the skier started off going in this direction with the initial velocity, and when the skier comes down and hits the ground, now the velocity is pointed this way. So that would be negative 39.7, and that goes in our table here. And that concludes the problem.